Okay. Hello everybody. And I don't see chat. Maybe, yeah, would be better to organize somehow. Not yet. Ah, yeah. Okay. Okay. Yeah. Thank you. So, last lecture we completed the material which is usually taken as a subject of a kind of midterm exam. So in Moscow Institute of Physics and Technology, there is a tradition during first semester of classes in analysis. There is so-called colloquium that is a little bit similar to midterm exam. What is standard in Western countries. There is a difference. First of all, this is an oral examination. Secondly, the material of exam will be not excluded from the material of final examination. So the main goal is to give a possibility for students to understand what is the system of exams in our institution. And so that is a part of, rather small part of the total sum which will define the final grade. And so the material which will be included into the program for this midterm exam ends on the inverse function theorem. So I'll send to everybody the list of questions which are the subject, and the midterm exam will be taken during classes. So I hope we'll be able to do it together with your seminars teacher. So we'll discuss more precisely the date of that term exam. I guess it will be in 2 weeks. So after 14th of December, approximately. But that is preliminary announcement. Okay, now we proceed with our material. So today is lecture number, what is number? I think, just a minute, 13, 15, 17, I think 18, right? 18, lecture 18 today. Yeah, I think so. So section 18.1, uniform continuity on the segment. And the main theorem here is counter theorem, which says if f is continuous on a segment AB, then f is uniformly continuous on AB. So for the segment, uniform continuity follows from, yeah, somebody helped me with the number. Indeed, it's 18. Yeah. Okay, so proof. Let me recall the definition of uniform continuity. For arbitrary epsilon greater than 0, there exists delta greater than 0 such that for all x1, x2 in AB, which satisfy the inequality x1 minus x2 less than delta, we have the inequality f of x1 minus f of x2 less than epsilon. That is the definition of uniform continuity. We want to prove that this is valid for our function f once f is supposed only continuous, not uniformly continuous. So, and we'll prove it by contradiction. So by contradiction. Suppose the opposite is valid, the opposite assertion is true, so there exists epsilon such that for all delta positive, there exist two numbers x1, x2 in A, B, which satisfy the inequality modulo x1 minus x2 less than delta, and the opposite inequality holds. That is contradiction, right? Our supposition, which is opposite to what we want to prove. Okay, now let me denote here as epsilon naught to underline that this is a fixed, so somehow it exists, right? Now, typical consideration which we applied many times, in fact. So once we have something is valid for arbitrary delta, let us put delta equals to 1, then delta equals to 1/2, and so on, delta equals to 1 over n, and so on. So infinitely many values of delta, as small as we want. And, okay, we may choose just 1 over n, let's say, right? So, for every choice of delta, like that, we can find two values of x1 and x2, and I'll denote them as, let's say, x1 1, x2 1 in AB, which satisfy model x1 1 minus x2 1 less than our first choice is 1, right? And f of x1 1 minus f of x2 1 in modulus greater or equal epsilon naught. And this choice can be realized for every value of delta from this list. So here there exists x1 2, x2 2 in AB, and again we have this inequality such that, okay, let me put it in brackets to separate from the final inequality. And we continue up to infinity. There exists x1 n x2 n in AB, model x1 n minus x2 n less than 1 over n, such that f of x1 n minus f of x2 n greater or equal epsilon naught, and so on. So that is an infinite process. Hence we have constructed two sequences, x and 1 in AB and x and 2 in AB. So there are two sequences of points of our interval. Now look at the first sequence. Oh, sorry. I mixed in notations. I am very sorry. Yeah, we put n up, not down. Sorry. Okay. Now look at the first sequence, x1n. That is a sequence of real numbers from a segment. Hence, this is a bounded sequence. Bounded sequence of real numbers. So, by Bolzano-Weierstrass theorem, we can find a subsequence. There exists x1 and k from 1 to infinity, which has a limit of x1 and k equals to x naught. Moreover, from the inequalities so all members of our subsequence x1 and k are between a and b because they are in the interval. And by properties of the limit of sequences, the limit of that sequence is also between. So we deduce that x naught is also between a and b. Now, f is continuous on AB, hence it is continuous at arbitrary point. So in particular it is continuous at x naught. F is continuous continues at x naught, then by Heine definition of continuity, limit as k tends to infinity f of x1 and k is equal to the value of f at x naught by continuity, right? Now, look at the inequalities for x1, x2. So what we know for arbitrary k natural, we have inequality x1 and k minus x2 and k is less or equal 1 over nk. Or I may rewrite it as follows. Just open modulo sign. So x1 nk minus 1 over nk less or equal, strictly less than x2 nk, strictly less than x1 nk plus 1 over nk. Now, as k tends to infinity, the left and the right hand sides tend to, x naught, because 1 over nk is strictly increasing sequence of natural numbers, so it tends to infinity in k. Hence 1 over nk tends to 0, right? So the left hand side and the right hand side tend to x naught, and by two policeman theorem, the middle tends to x naught as well, right? Look, now again by continuity, so from this fact, by continuity and by Heine definition, we deduce limit as k tends to infinity f of x2 and k is also f of x naught, right? But then it follows from those two that the limit as k tends to infinity f of x1 and k minus f of x2 and k is equal to 0, because both limits coincide, so the limit of difference is 0. But from the other side, for arbitrary k, we constructed our sequence in such a way that modulo f of x1 and k minus f of x2 and k is greater or equal than epsilon naught. But those two contradict each other, right? And that's all. The theorem is proved. Okay. So now let me consider a couple of examples, but they are given in your lecture notes, but I will consider them in a different way, slightly. So, example 1. F of x is equal to square root of x on 0 infinity. On 0 infinity. We considered before, during last lecture, square root of x is uniformly continuous. So the question is it uniformly continuous? Or not? Square root of x is uniformly continuous on 1 infinity, I think, if I remember correctly. We considered such an example. Square root of x is uniformly continuous on 1 infinity. Example from section 17.2 from the last lecture. Yeah. Now, square root of x is continuous on 0, 1, hence by theorem, counter theorem, just proven, we have square root of x is uniformly continuous on 0, 1. Now we can deduce from those two facts that square root of x is continuous on 0 infinity. Why? Because, look, so square root of x is uniformly continuous on 1 infinity. What it means? For arbitrary epsilon, there exists delta 1, I'll denote it, such that for all x1, x2 from 1 infinity, which satisfy the inequality x1 minus x2 less than delta 1, we have square root of x1 minus square root of x2 less than epsilon over 2. Next, square root of x is uniformly continuous on 0, 1. Analogously, for arbitrary epsilon, there exists delta 2 greater than 0, such that for all x1, x2 from 0, 1, which satisfy the inequality x1 minus x2 less than delta 2, we have square root of x1 minus square root of x2 less than epsilon over 2. Now, put delta equals to minimum of delta 1, delta 2. Then, for arbitrary x1, x2 from 0 infinity, which satisfy the inequality x1 minus x2 less than delta, what we can deduce? So for arbitrary values of x1 and x2, which are located near each other, right, close, difference between them is less than delta in modulus, what we have? Okay, there are several possibilities. So, first case. If both x1 and x2 let's say in 0, 1. Then, of course, look, both x1 and x2 are in 0, 1, and the difference is less than delta. Hence, it is less than delta 1. Sorry, delta 2, right? Delta 2. Hence, the difference between square roots in modulus is less than epsilon over 2, which is less than epsilon, of course, right? Analogously, we can consider the case x1, x2, both from 1 infinity. Again, same conclusion. And the third case, which is okay, in fact, better to say I should consider 4 cases, because let's say x1 from 0, 1 and x2 from 1 infinity, right? And fourth case when we have other combination, x2 from 0, 1, x1 from 1 infinity. But of course, last and that is why delta should be minimum, because now look, even from those two, it's clear why delta should be minimum. Because if x1 and x2 are from 0, 1 and both satisfy the inequality x1 minus x2 less than delta, then x1 minus x2 is less than delta 2, because delta is minimum of delta 1 and delta 2. So modulo x1 minus x2 less than delta implies the inequality x1 minus x2 less than delta 2. So this is true, hence square root of x1 minus square root of x2 is less than epsilon over 2. Same for the second. Is it clear? Okay, now for the third case. Also here it works, by the way. I mean minimum. Look, now we deduce that both x1 minus 1 is less than, okay, from 0, 1 than delta 2, and 1 minus x2 is less than delta 1. Look, if x1 minus x2 is less than delta, so let's 0, 1, so x1 is somewhere here, x2 there, right? x1 in 0, 1, x2 in 1 infinity. Difference between them in modulus less than delta. Hence, difference between x1 and 1 and between 1 and x2 is less than delta as well, right? And what we need, that x1 minus 1 is less than delta 2, and 1 minus x2 is less than delta 1. Okay? Clear. Okay. Yeah. And now, what we deduce? We deduce that square root of x1 minus 1, which is square root of 1, less than epsilon over 2, and square root of x2, sorry, start from 1. It doesn't matter, of course, but less than epsilon over 2, right? Because here we have a conclusion for arbitrary such x1 and x2. So I take x1 is x1 and x2 is 1 temporarily. And from those two inequalities follows square root of x1 minus square root of x2 by the triangle inequality less or equal than square root of x1 minus 1 plus 1 minus square root of x2 less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. So that is epsilon is epsilon over 3. Why epsilon over 3? No, not necessarily. Of course, you can choose epsilon over 3 if you want, but you see that here we have less or equal, right? But next, using, we have strict inequality, epsilon over 2 plus epsilon over 2. So that is strict inequality, so no problem. I mean, of course, you can choose epsilon over 3 if you want, right? But not necessarily, because here we have strict inequality, so it's okay. No. Yeah, and that's all. So that's, we have proved this square root of x is continuous on 0 infinity. That's it. Okay, and now also useful fact, which is formulated as a theorem. So theorem, Cantor theorem was theorem 1. Theorem 2, in fact, I would say that is a problem, so solution, good problem in fact, but in your lecture notes it's given as a theorem, so let it be a theorem. Although I would say good exercise. So theorem. F is uniformly continuous on an interval AB. Okay, let AB are both finite. If and only if F is continuous on AB and there are finite limits. Limit x tends to a plus f of x and limit is x tends to b minus f of x. That's it. Okay. Okay. Proof. Let's prove firstly sufficiency part. Sufficiency. So this condition is indeed sufficient. Why? So put f tilde of x by definition is the following. F of x for x from interval, limit of f of x as x tends to a plus when x equals to a, and the limit as x tends to b minus f of x if x equals to b. It is a new function which is defined on the segment AB, right? Moreover, it is continuous at every point. Why? Because for in the point of the interval f tilde coincides with f and continues because of continuity of f. For the point x equals to a, it is continuous from the definition. So f tilde is continuous on the segment. Hence, by counter theorem, f tilde is uniformly continuous. On AB. And if f tilde coincides with f on the interval, right? Hence, f is uniformly continuous on AB, just from the definition. So sufficiency part is proven. Necessity. Let us write down uniform definition, or uniform continuity definition. For arbitrary epsilon, there exists delta such that for all x1, x2 from the interval AB, which satisfy the inequality x1 minus x2 less than delta, we have the inequality f of x1 minus f of x2 is less than epsilon. Now look, what we have to prove? We have to prove that there exist finite limits. And look at this chain of quantifiers. So from this follows that for arbitrary x1, x2, which satisfy the inequality A, so in A plus delta, we have same inequality. Because if both x1 and x2 are in that right hand side neighborhood of A, then they satisfy this inequality, right? So, but this chain of quantifiers, what is underlined, implies by Cauchy criterion that there exists finite limit as x tends to a plus of f of x. And analogously, we can prove the existence of the right limit. That's it. Okay, let's have a break. let's continue. So now section 18.2, second remarkable limit. Here, in fact, the situation with the first and the second remarkable limits is quite different. I mean, no question about what is the first remarkable limit. Everybody agrees this is sine x over x, as x tends to 0. But for the second remarkable limits, there are different opinions, and I prefer to consider definition of E as a definition of E. This is a limit of a sequence which we considered before. There was a special section about the number E, and the number E was defined as a limit of such a sequence. Now, we want to generalize this, and in fact, theorem which I would prefer to call the second remarkable limit is the following. So, theorem 1, the limit as x tends to 0, 1 plus x power 1 over x equals to E. And before to start the proof, I would like to discuss a little bit what means a power, right? So, let me give a sketch of the construction of exponential function, so, and its properties. I'll not go into details, but I would like to mention the problem. So, let us start with x to the power n. F of x equals to x to the power n. For x from 0 to infinity. If n is natural, then f is continuous, and strictly increasing. On 0 infinity, right? Hence, it has an inverse function. The inverse function, f minus 1, is continuous and strictly increasing. On 0 infinity, which is just f of 0 infinity. And what is inverse function to x to the power n? That is nth root, right? So f minus 1 of y is nth root of y. Hence, we defined what is nth root rigorously, And of course, we can check all properties of nth root. I mean, nth root of product and so on, so on, so on. Then we can proceed further. Now we know what means x to the power p over q, where p over q is a rational number, right? What it means. So if that is p is natural, q is natural, then it's clear what is it, right? That is root of x, qth root, power p, right? So when both are natural, it's okay. Then if p is negative, let's say, then okay, again we know what is it. If p is integer but not natural, then q is natural, then x power p over q is 1 over x to the power minus p over q. Again, by definition. So now we know what means a to the power x is defined, that function is defined, f of x, a to the power x, is defined for all values x in q. That is for a greater 0, right? Of course, we should exclude 1 if we want to have strictly monotonicity, but that is not necessary. So, now power function is defined for all rational values of x. Of course, this is strictly increasing function, and since it is strictly increasing, there are limits. I mean, for arbitrary x in R, there is a limit as, let's say, x naught in R, x tends to, let's say, x naught minus x in rationals of a to the power x, because that is monotonic sequences are considered here. And that is by definition, is a to the power x naught. Of course, you need to check that this definition is correct. Then you need to check if all properties of exponential function which you study in high school are valid indeed. And that is a very, very long story, in fact. I'll not do it. So we'll skip this part of standard analysis course. I mean, to check that indeed power function is well defined, it satisfies all properties which you know, and in fact it is continuous function everywhere, right? And by the way, once you have continuous strictly increasing functions, then you can consider inverse function, and inverse function is logarithmic function, right? So we can define logarithmic function. Also, we prove that logarithmic function is continuous, and in the future we'll use those facts, but as I told, we skip details. Now let us prove the theorem. So now this power is well defined, and we can prove it. So, proof. Firstly, we'll prove limit as x tends to plus naught. Or 0 plus, doesn't matter. Let's choose 0 plus. 1 plus x power 1 over x equals to e. If we'll denote x equals to 1 over t and use limit of a composite function, so then that is equivalent to say limit as tends to plus infinity 1 plus 1 over t power t equals to e. That is 1 over x equals to t, right? And here is plus infinity. I would mention that in your lecture notes, limit as x tends to infinity in theorem 4.10.1 is understood in a different way than it was understood before. That's important. But I don't want to introduce two different understanding of the same notation. So we'll use same notation, same understanding as it was before, not a new one. Okay, so the limit as t tends to infinity, 1 plus 1 over t power t is equal to e. That is what we want to prove, right? Okay, we'll use Heine definition. So Heine definition. We take arbitrary sequence Tn, n from 1 to infinity, limit as n tends to infinity Tn equals to infinity, plus infinity, in fact, right? Then consider integer part, then integer part of Tn less or equal Tn less than integer part of Tn plus 1. So what we deduce, 1 plus 1 over Tn then is between what? Less or equal 1 plus 1 over integer part of Tn, right? And greater than 1 plus 1 over integer part of Tn plus 1. Of course, we need to be a little bit careful. I mean, yeah, here integer part can be equal to 0, right? But if we have Tn tends to infinity, then for sufficiently large n, Tn will be greater than 1 for sure, right? Hence, for sufficiently large n, this is well defined, so no problem. By the way, same problem appears in 1 over Tn. Okay, then it follows from this we can take arbitrary power. So okay, I will write maybe two chains. Okay, first 1 plus 1 over Tn power Tn, right? Less or equal than 1 plus 1 over integer part of Tn power Tn. That is from the properties of the function x to the power Tn. So this function is strictly increasing for Tn positive, and hence we have this inequality. Now, because of properties of exponential function, we can replace here by something larger, and it gives integer part of Tn plus 1. That is 1 plus 1 over integer part of Tn power integer part of Tn, right? And times 1 plus 1 over integer part of Tn. Okay, just this one. And I don't remember precisely how it was called. We considered, when we considered definition of E, there was a theorem about that for arbitrary sequence of integers we had this also, right? For arbitrary Pn in n in even in z, I guess, right? Pn tends to infinity. It was plus minus infinity, I guess. We consider it like that. If I remember correctly, there was a theorem. I forget to check it. I think it was. Let me. I should refer. Okay, so maybe I'll avoid reference to the theorem because it is not so difficult to reconstruct. I didn't see a reference to the theorem. It seems to me there was. I'm not sure. Okay. And so that is an estimate from above. Now below, estimate from below. 1 plus 1 over Tn power Tn is greater than 1 plus 1 over integer part of Tn plus 1 power Tn, greater or equal 1 plus 1 over integer part of Tn plus 1 power integer part of Tn, and I'll rewrite it as 1 plus 1 over integer part of Tn plus 1 power Tn plus 1, right? Divide by 1 plus 1 over integer part of Tn plus 1. Now, look. The line under integer. The line under then integer under this, look, okay, maybe I'll give more details. So if Tn is between that, then 1 over Tn is greater than 1 over into the part of Tn plus 1, less or equal than 1 over into the part of Tn, and that is because of this. So if limit of Tn is infinity, then Tn for sufficiently large n are positive for sure. That is why we get this inequality from properties of division. And then, so that follows, and then this one. We add 1 to each part. Is it okay? Okay, I hope it's okay. Now, look, I claim that, so the limit as n tends to infinity, 1 plus 1 over integer part of Tn power integer part of Tn is same as limit as n tends to infinity, 1 plus 1 over integer part of Tn plus 1 power Tn plus 1 equals to e. Why? Okay. Why? Because of, as I said, I'm not sure if I forget. Simply I forget if I proved it or not. So, in fact, I'll prove even more that the limit 1 over Pn power Pn equals to e for arbitrary sequence Pn of naturals such that limit of Pn is infinity. That is a claim, and after that, in fact, the first part will be proved. Why? I mean that one. Because for arbitrary sequence, now the estimate above tends to e, and estimate below tends to e as well, because those are parts of that claim, and those terms tend to 1. So by two policeman theorem, we obtain the desired result. So two policeman theorem imply the limit as n tends to infinity 1 plus 1 over Tn power Tn is equal to e. That is what we want to prove for this part. So let us prove that claim. From the definition of E, what follows? From the definition, just from the definition. For arbitrary epsilon greater than 0, there exists number n, natural, such that for all n greater than n, we have an equality 1 plus 1 over n power n minus e less than epsilon. Now, from the inequality that limit of Pn equals to infinity follows that there exists, let's say, capital N1 natural, such that for all n greater than n1, we have Pn greater than everything what we want from the beginning, right? And let us choose, it should be greater than capital N. Capital N is precisely that one. Now look. So take arbitrary epsilon greater than 0. We have found capital N natural, right? Then we have for all n greater than capital N1, it means that in fact we have found N1 natural. That is what is better for us now. Look, for arbitrary epsilon, we have found capital N1 such that for all n greater than capital N1, we have Pn greater than capital N, and Pn is natural. And hence, look, Pn is greater than capital N, hence 1 plus 1 over Pn power Pn minus E is less than epsilon. That is what we want. So what is underlined twice? For arbitrary epsilon, we have found capital N1 natural, such that for all n greater than n1, we have 1 plus 1 over Pn power Pn minus E less than epsilon. That is precisely our claim. And it means the first part of the proof is over. So t tends to plus infinity. The second part is, okay, so second part is about the limit as x tends to 0 minus 1 plus x power 1 over x equals to E. That is the second part. So what we want to prove now is this one. So let us rewrite it in a different way. How? Denote y equals to minus x. So what we want is now limit as y tends to 0 plus 1 minus y power minus 1 over y equals to E. That is what we want to prove now. So I'll put questions to specify what we don't know yet. Okay, now look at this expression. So what is it? That is 1 over 1 minus y power 1 over y. Then I'll rewrite it as 1 over 1 minus y power 1 over y. That is 1 plus y over 1 minus y. 1 over y. And let me rewrite it as follows. So that is one plus y over 1 minus y power 1 over y over 1 minus y. And I should, that is like that, so times not good. Times 1 over 1 minus y. And that is like that. Okay, so now now I'll use, in fact, I can use continuity, that's it, of logarithmic function, yeah. So, look, what we have here. We have, if we denote y over 1 minus y, let us denote it by, which letter was not used? U, right? So y tends to 0 plus is equivalent to u tends to 0 plus. Then the limit as y tends to 0 plus 1 plus y over 1 minus y, 1 over y over 1 minus y is equal to limit as u tends to 0 plus 1 plus u power 1 over u, and that is, we know what is it. That is e by the first part, right? Now I can rewrite everything as follows. Let me write it here. Let's say equals to let's write it here, right? I can write like that. That is e to the power 1 over 1 minus y times logarithm of this bracket, this power, y 1 minus y power 1 over y over 1 minus y. Yeah, now we know that logarithmic function is continuous everywhere. That is 1 over y I think 1 minus y over y. Yes, yes, it's true. And why this question, please? Because I used it. One over y plus 1. Is it better? Ah, yeah, it's easier. You're right. It's easier. Yeah, thank you. It's a little bit easier. Okay, let me firstly finish with this proof. So we know that logarithmic function is continuous. Now we know the argument tends to e, right? Hence logarithm tends to 1. Here tends to 1, so tends to e, as y tends to 0 plus. But maybe indeed it's a good question. Let me use it. Okay, it's slightly different here, right? So if we'll use this 1 over y equals to 1 over y over 1 minus y plus 1, right? That is also is true. So instead of product, we can use here an easier thing, namely plus. So put here plus 1, right? And then that is equal to 1 plus y over 1 minus y power 1 over y over 1 minus y times 1 plus y over 1 minus y. That's it, right? So this tends to e, and that tends to 1, as y tends to 0 plus. That is another way. So, yeah, indeed, of course, if we put here sum, it's easier than to use product. But with product, you can proceed like that. That is also true. Thanks for your question. Good, very good. Very good. Yeah. Okay, yeah, and it's time to stop. And in fact, you see that we have proved the second part, hence we proved the second remarkable limit completely. Okay, that's all for today then. Thanks for your attention, and thanks for good idea. Thank you. Okay.